Hey everyone, and welcome to this explainer. Today, we're setting a very deliberate, highly focused pace because we are exploring the hidden electrical forces that literally power everything around us, from the smartphone in your hand to the massive global power grid. We're going to take a really deep dive into the fascinating world of electrical transients and AC circuits. And look, I promise you, by the time we wrap up, we're going to go way beyond just memorizing dry formulas. We are going to truly visualize how components like capacitors and inductors behave, how they breathe life into a circuit, and exactly how they react to the invisible forces of time and frequency. So get comfortable, focus in, and let's decode the hidden behaviors of these incredible components. To really kick things off, I want to pose this fundamental question straight from our study guide. It might sound a bit basic at first, but really think about it for a second. Can you explain how electromagnetism actually works in a circuit? It's one thing to understand that a battery pushes current through a wire, but what happens when that flowing current creates a magnetic field? Or what about when an electric field holds a charge entirely on its own, just waiting there? Challenging your current understanding with this exact question is exactly how we unlock the deeper, much more fascinating mechanics of electricity. Here is our cognitive roadmap for today. 1. Meet the energy storers. 2. Time constants and transients. 3. Reactants in AC circuits. 4. Phase shifts and phasors. And finally, 5. Series, parallel, and impedance. Let's jump right into section 1. Meet the energy storers. Okay, let's dive into this and decode the foundational DNA of these core components. Now, notice how a resistor basically just opposes current and dissipates that energy as heat. Pretty straightforward. But as we move down the list, things get interesting. Capacitors store energy in an electric field, specifically concentrated in the dielectric material between two plates. Think of a capacitor almost like a water tower, storing up pressure, holding on to all that potential energy, just ready to be unleashed into the system at a moment's notice. Inductors, on the other hand, store their energy in a magnetic field, which is concentrated within the turns of a wire coil. So instead of a water tower, they act much more like a heavy, spinning water wheel that carries this massive amount of physical momentum. They are completely different storage mechanisms, yet, as you'll see, they act as the essential counterweights to each other in absolutely all of electrical engineering. And that brings us to the single biggest takeaway when comparing these two. A capacitor's primary function is to actively oppose a change in voltage. If the voltage in a circuit tries to spike suddenly, the capacitor acts like a giant shock absorber and just absorbs it. But if the voltage drops, the capacitor jumps in and supplies it back to the circuit. Conversely, an inductor's primary job is to fight changes in current. If you try to suddenly stop the current flowing through a coil, the inductor's magnetic momentum is going to push back forcefully to keep it flowing. So, capacitors fight voltage changes, while inductors fight current changes. It really is this beautiful, symmetrical rivalry. All right, moving right along to section 2, time constants and transients. What's really interesting about this slide is the incredible mathematical precision of this charging curve. When you close a switch on a resistive capacitive, or RC circuit, the voltage doesn't just jump instantly to its maximum level. It has to climb, and the formula predicting this climb is elegantly simple. Time equals resistance multiplied by capacitance, or T equals R times C. But here is the kicker. Exactly one of these so-called time constants represents the specific moment the voltage reaches exactly 63.2% of its maximum value during its initial rise. Now, why 63.2? Well, that specific percentage isn't random. It's derived purely from Euler's number in mathematics, which represents the natural rate of exponential growth and decay in the universe. It's almost like a universal speed limit. It takes exactly 5 of these naturally derived time constants for the capacitor to reach 99%, which is essentially a full stable charge. Now, deliberately comparing an RC and RL circuit reveals this fascinating mirror image. Let's look closely at the red current lines. In the charging capacitor, it draws this massive spike of high current right at time 0, which then slowly tapers off as the voltage builds up and pushes back. Now look over at the inductor. It behaves in the exact opposite manner. The inductor forcefully holds back the current at time 0, generating a massive spike of voltage initially to oppose the change. And only then is the current slowly allowed to build up its momentum. It literally is a perfect mathematical mirror image of transient behavior. Let's shift gears now into section 3, reactants in AC circuits. To really understand AC circuits, we have to master this concept called reactance. Think of reactance as the AC version of resistance. It's still measured in ohms, but it comes with a massive dynamic twist. Unlike standard resistance, which just stays exactly the same no matter what's happening, a capacitor or inductor's opposition to current actively changes depending on the AC frequency. For a capacitor, a higher frequency means less opposition. But for an inductor, a higher frequency means more opposition. The frequency of the wave entirely dictates how hard the component pushes back. And this precise frequency-dependent behavior, that is exactly how radio tuners can filter out thousands of unwanted stations to lock on to just one specific broadcast signal. To actually visualize what alternating current does to a capacitor, we have to look at the relentless oscillating nature of a sine wave. Because the AC wave is always changing, the capacitor is literally never allowed to just sit at a steady, comfortable charge. As the AC voltage increases positively, the capacitor charges up. But the second the voltage peaks and starts decreasing, the capacitor discharges right back into the circuit. Then, the AC wave drops down into negative territory, and the capacitor actually charges up again, but completely in reverse polarity. It is a continuous, high-speed cycle of charging, discharging, and violently flipping directions dozens or even hundreds of times every single second. Which naturally brings us to Section 4, phase shifts and phasors. Because of all of this continuous charging and discharging we just talked about, we have to introduce a pretty complex reality of AC circuits. When you have capacitors or inductors in the mix, the voltage waves and the current waves do not peak at the same time. They fall out of sync. To keep track of this shifting, engineers use this classic, highly memorable mnemonic, Eli the Iceman. If you can remember this simple phrase, you will instantly recall the specific 90-degree phase shifts of these components with absolutely no heavy mental lifting required. So let's decode exactly how to read it. Let's anchor to the Eli portion of our mnemonic first. In the word Eli, the E stands for voltage, specifically electromotive force, the L stands for inductor, and the I stands for current. Reading it straight left to right tells us that in an inductor, the E comes before the I. You can clearly see how the input voltage wave peaks exactly 90 degrees before the current wave even reaches its maximum. The voltage is leading the current, basically dragged out of sync by that powerful magnetic field. And this brilliantly illustrates the ICE part of the trick. In the word ICE, I stands for current, C stands for capacitor, and E stands for voltage. Here, I comes before E, meaning in a capacitor, the current leads the voltage by exactly 90 degrees. Why does this happen? Well, because capacitive current depends strictly on the rate of change of the voltage. When the voltage is crossing the zero line, it's actually changing at its absolute fastest physical rate. That means the current flowing into the capacitor is already at its maximum peak. It is such a brilliant, elegant interaction. All right, we've made it to the final stretch. Section 5, series, parallel, and impedance. Now we are going to combine resistance, capacitance, and inductance all together in one circuit to find the total load. But to solve a combined circuit like this, we need a brand new concept, impedance, which is represented by the letter Z. Impedance is the resultant total opposition to current flow in an AC circuit. But guys, here is the trick. Because of those 90-degree phase shifts we literally just explored, you cannot simply add 100 ohms of resistance to 100 ohms of reactance, like normal math. 100 plus 100 absolutely does not equal 200 here. Because they are completely out of phase, they have to be added together as vectors. It's kind of like a giant puzzle, and this right triangle is the master key to AC math. The horizontal line represents pure resistance. The vertical line represents our reactance, and it's drawn pointing straight up specifically to account for that exact 90-degree phase shift. To find the total impedance, our Z, we have to calculate the hypotenuse of this right triangle using the Pythagorean theorem. So if your resistance is 100 ohms and your reactance is 100 ohms, you combine them vectorially, you take the square root of 100 squared plus 100 squared, and you get a total impedance of 141 ohms. The physical geometry perfectly dictates the electrical reality. How cool is that? Summarizing all these complex formulas reveals some really stark differences in circuit structure. Don't get lost in the raw math here, but just notice how finding the total voltage, current, and impedance shifts dramatically depending on whether your circuit is wired in series or in parallel. For example, in a series circuit, you calculate total impedance by vectorially adding the ohms, but in a parallel circuit, you have to find the total current first by vectorially adding the parallel branch currents. The actual physical layout of the wire entirely dictates the mathematical path you have to take to solve it. To wrap up our comparative journey today, let's really lock in these fundamental takeaways for AC circuits. When you place components in a series circuit, they all share the exact same current. Therefore, we use the current as our baseline reference to mathematically align all those shifted voltage waves. But when you place components in parallel, they all share the exact same source voltage. So we use the voltage as our reference point, and it's the individual current waves that shift around. The golden rule here is to always look at what the components share to ground your perspective. As we finish up, I want to leave you with this provocative thought to ponder. Our source material points out a totally mind-bending fact. Ideal capacitors and inductors dissipate strictly zero power, literally none. They just borrow energy to build up their fields, and then they return it all completely back to the circuit. All the true power dissipation happens only in the resistance. So think about this. If the source voltage and source current are knocked completely out of phase by these reactive components, how much true usable power is actually being delivered? Well, it turns out you have to multiply volts times amps times the power factor, which is dictated by that exact phase angle. Next time you flip a switch, think about how the microscopic phase relationships you just visualized dictate the efficiency of the massive energy grids powering the world around you right now. Thank you so much for joining me on this deep dive. I hope it sparks some curiosity.